Okay, well, good morning and welcome. I'm delighted to see so many 3D people in the same place. Thank you for coming. I know COVID is still around, and so it does take a little bit of effort to get on the plane and come, but it's really great to see you all. I'm delighted to be here myself and to see everybody. I'm Frank Van Diggelen, the ION president, and so it's my pleasure to formally welcome you to ION's ITM PTTI 2023 conference. Before I get started with announcements and introductions, I want to advise you that this session is being recorded, the audio and the slides, for broadcast to ION's virtual audience and to be hosted on ION's YouTube channel. So please be mindful of this in your in-room conversations. The audio equipment is very sensitive, and so what you think is a quiet, private conversation might not be. And regarding the conference sessions that follow this, I want to remind you that recording of those sessions by you is not permitted. Please refer to the on-site programs for ION's policy on photography and audio and video recording of sessions. During the sessions, please remember to put your phones and other electronic devices to vibrate or silent or off. ION is a membership organization, and becoming a member may be one of the most valuable things you do for your career in 2023. This is a terrific place for recruiters to recruit people and to get recruited. To make it easier for new people to ION to learn about us, we're running a membership special for those of you who are attending this meeting as a non-member. If you are wearing a name badge that has a yellow stripe on it, it means you are eligible to join ION for an introductory price of $15, 15. That's less than what a sandwich costs up there in the lobby. Please see the registration desk for more information. I'm happy to report that for a full year now, ION's technical journal, Navigation, has been open access. This means that the research published in Navigation is available free of charge to a worldwide audience. We have put a lot of effort and resource into making Navigation the world's premier position navigation and timing journal, and we encourage you to check it out and share with your colleagues. The journal is indexed in many international services, but the easiest way for you to access it is through our website, ion.org/navi, N-A-V-I. ITM and PTTI are co-located meetings, the advantage of which is that you, as an attendee, are free to move between all the available sessions and download sessions from either conference. So now I'm very pleased to introduce this year's Technical Program Committee. There are 6 people, but I will, 5 people I will introduce. The ITM General Chair, Dr. Juan Blanche, is a senior research engineer at Stanford University, where he works on integrity algorithms for space-based augmentation systems and on RAIM. He received the 2004 Parkinson Award for his doctoral work on ionospheric estimation for SBAS, and the 2010 Early Achievement Award from the Institute of Navigation for his work on advanced RAIM. Dr. Blanche, we're over there. Thank you. So Dr. Blanche is the general chair. The ITM program chair, Dr. Andrei Soloviev, is a principal at QNAV. Previously, he served as a research faculty at the University of Florida and as a senior research engineer at the Ohio University Avionics Engineering Center. He holds BS and MS degrees in applied mathematics and physics from the Moscow Institute of Physics and Technology and a PhD in electrical engineering from Ohio University. His research interests focus on all aspects of GNSS signal processing and estimation, as well as multi-fusion for navigation applications. He is a recipient of the ION Early Achievement Award and the RTCA William E. Jackson Award. Dr. Soloviev, thank you. So those are the ITM General and Program Chairs. The PTTI General Chair, Dr. Sven Christian Ebenhag, is a senior scientist in photonics and implementations of time and frequency transfer over a national fiber communication network at RISE. the Research Institute of Sweden. He is also working for Big Science Sweden with the goal of increasing Swedish presence at 13 international research facilities. Dr. Ebenhaag received his PhD in photonics from Chalmers University of Technology in Sweden with a thesis on frequency transfer techniques and applications in fiber optic communication systems. Dr. Ebenhaag, thank you very much. And PTTI Program Chair, Dr. Daphne G. Enzer, is a member of the Frequency and Timing Advanced Instrument Group at NASA's Jet Propulsion Laboratory, where she recently led clock system modeling for the Deep Space Atomic Clock mission and was an integral part of the operations and analysis team. She is currently on the data analyst team for the Sun Radio Interferometer space experiment. She received a PhD in atomic physics from Harvard University. Dr. Enzer, thank you very much. And finally, the PTTI Tutorials Chair. I know many of you benefited and enjoyed the tutorials yesterday. The chair for those, Dr. Joseph Wojtek, leads a research department of optical networks at the Czech Technical University in Prague. He has been responsible for developing a family of open photonic devices, holds 13 patents, and participates in multiple international projects and studies. He is a past recipient of the Research Prize of the Czech Minister of Education. Dr. Wojtek? Well, we'll give him a hand. I'm not sure where he is. Now I'd like to turn this over to Dr. Soloviev, who will introduce our first plenary speaker. Thank you.
Well, thank you so much, Frank, for warm introductions. And welcome everyone to this year ITM and PTTI. So without further ado, I'm going to go ahead and introduce our first speaker, Dr. Han Park, who will talk about the perspectives and challenges of advanced air mobility, a very interesting and fascinating application. Dr. Park is currently the Deputy CTO of Supernal, an urban air mobility division of Hyundai Motor Group. Prior to Supernal, he was a Vice President of Engineering at Samsung Electronics, where he led autonomous driving and robotics programs. He received his BS in Mechanical Engineering from the University of California, Berkeley, an MBA from UCLA Anderson School of Management, and SM Mechanical Engineering from Massachusetts Institute of Technology, and a PhD in Aeronautical Engineering with a minor in Electrical Engineering from California Institute of Technology.
Thank you so much, Andre. It's really a pleasure to speak here. I have worked in the navigation area domain before, and I see some faces here. But it's been about, I guess, 7-8 years, probably, since I've actually been to an ION conference, and it's really wonderful to be back here. So today I'm going to talk about advanced air mobility, and not necessarily, and it'll be an overview. It's not going to be detailed about the navigation system itself, but I just thought it would be a great way to introduce what advanced air mobility is and what some of the challenges, including navigation, and love to have actually a discussion. So this is the agenda for today. So I'm going to talk about why and what is advanced air mobility. So it's now kind of become this generic term, but it has certain implications and what the domain is about. And in particular, then I'll talk about the urban air mobility, and that's the area that Supernal is working on, and what challenges are there in terms of the technologies, what is really driving this market, and what are some of the gaps. And then we'll talk briefly about our vision of how this will come together and give you a little summary. So what is advanced air mobility? It really is not one thing. It's about really the invention, or not the invention, but the maturation of a new technology which is the electric propulsion. Before, there was kind of limited ways you could build aircraft. Most of it is driven by propulsion technology, right? Whether it's a jet engine, it's the piston engine, propeller aircraft. But something new has happened, right? Just like electric vehicles that are coming out, EV vehicles that now you have sufficient range. But 10 years ago, you probably didn't consider electric vehicle because it had limited range and it didn't really fit your needs. But what's happened is that the battery technology continued to improve, and now you could buy a car, an electric vehicle with 400 or 500 mile range, which is basically equivalent to a conventional vehicle. And same thing is starting to happen with electric propulsion for aircraft. It's just right now on the margins where, maybe with a battery-powered aircraft, you could actually fly some useful missions. But also, it's very close to, like the Wright brothers. When the aviation industry started, you saw many different configurations of the aircraft. There was an explosion, right? And sort of Darwinism and other, right? You kind of converge to an optimal vehicle configuration, right? Now, in fact, before you could tell like airliners, right? That's a 747, that's a DC-10 or whatever, right? But now everything is a twin-engine aircraft, right? And it's just optimized now that's become now the optimal configuration. But it's not happened yet to electric vehicle propulsion systems. And so this is why you see this basically like a diversity of different aircraft, right? Everybody's trying to experiment with what is the optimal configuration. And this is what we call typically the advanced air mobility market. And we'll talk about the different segments of it, but this explosion of different types of vehicles that people are experimenting with. So, as I mentioned just in the previous slide, a lot of the things are being really, the propulsion system really drives the evolution of aircraft. So if I look at sort of from the first generation, as I mentioned, it was mostly the piston-powered aircraft. If we talk about the second generation, then the jet engine came about and started again a revolution in terms of speed, comfort, and we believe right now we're on the cusp of the third generation of propulsion system, which is the electric propulsion system. And if we look at some of the characteristics, if we start, let's say, just from the power density, you see actually, if you do the math, actually a reciprocating engine and a jet engine, actually, if you talk about power density in terms of weight, are not that far off, actually. So you say, well, because most people think jet engines, they must be so much more powerful than piston engine aircraft, but it actually isn't that much more powerful. But what is different, actually, is you can see the time between overhauls and service. And this is what really drove the jet engine, which was, with a reciprocating engine, you have a lot of wear and mechanical wear, you have to change the oil, etc. But with the jet engine, which is like an axial flow type, just a smooth rotating motion, so it really reduces the amount of maintenance that needs to be done. And we feel the electric propulsion is doing something similar too. Again, just if we look at the motor and the power density, in fact, it is about an order of magnitude denser in terms of power than either the piston engine or the gas turbine. And this is what's also exciting for people. You can see also in terms of between time to overhaul and inspection, we're talking another order of magnitude, potentially, maybe not as an order, but certainly many factors above more of the conventional power systems. So this is why people, and of course there's also the eco-friendliness. Of course you do have to charge the batteries, but again, it's similar to EV vehicles, that it's a very low emission vehicle. So I mentioned that now that you have this very high power density for your propulsion system, it also now frees you up in terms of different configurations that you can build an aircraft in. So normally if you had a jet engine or whatever, they're relatively large systems, so you had to put them in certain places. So it limited the type of configurations you could build. But now that you have these compact motors, you can put them basically anywhere you want on the aircraft. And this is, again, the explosion of different types of vehicles. By the way, a lot of it is material is sort of borrowed from different companies, and this is meant to be a general talk. So I have been giving credit, so you'll see the credit that different companies have produced some of these figures. So we can start from things like multicopters. These are basically like helicopters, or you can think of them like as DJI drones or optocopters. These are more like, let's just scale that up. Right? That's the idea there. There's also a lift plus cruise. This is a configuration where really, in theory, it's a very simple configuration. You use the lift rotors to lift yourself, and you have propellers to push yourself, right? So it sounds really simple, right? Like, that's the easiest thing I can build, right? It turns out that's not the easiest thing to build, but for a lot of people, okay, there's simplicity in that. By the way, before I joined Supernal, I was not in the rotorcraft community, so just to clarify, and I also learned this, rotors are or for laymen, like propellers that actually produce thrust up. Propellers are things that produce thrust going forward, right? So when I talk about rotors and propellers, you might get like, what's he talking about? So they're basically, the shape is basically similar or the same, but they produce thrust in different directions. So I'll talk about also prop rotors, right? So when we talk about tilt rotors, they're actually called prop rotors because they can tilt and produce thrust up or thrust forward. So this is a tilting mechanism. Like the most famous example would be something like a V-22. And this is another configuration. This is so-called a ducted vector thrust. Sometimes tilt rotors are also categorized as vector thrust. And this is more smaller, enclosed propellers. So the other ones are on the left side, maybe on your right side, are what they call characterized as open rotors. So the rotors are exposed, and then you also have duct. The ducting has some advantages. You can take advantage of entrainment and other things, but it also has huge challenges too. Anything like inlet distortion and other things can quickly destroy the efficiency of the propulsion system. So this is another perspective of what is the most efficient configuration. So it actually depends again. Right? Everything is a series of compromise. So I guess to your left, or right, sorry. No, it is the left. So these are on the axes, the vertical axis is the hover efficiency. So if you were trying to, how much power does it require to actually stay aloft? And the x-axis is the disk loading, meaning how much thrust are you generating per area. So what you want to do when you want to be hovering, you want as low as disk loading as possible. So helicopters, you can see that it sweeps a very large area, and you're moving basically a volume of air very slowly down. And that's the most efficient way to hover. But that's not always the configuration that you can have. But the problem is that you're very slow when you're a helicopter. You have very high good efficiency, but you want to fly fast, right? So the other extreme would be something like an F-35, right? Where you basically have jet engines. It's actually a combination. F-35 actually has a lift fan also generating thrust down, but maybe the older Harrier style just had these jet nozzles. But they're very poor at hovering. They can go fast, but they're very poor. In fact, you don't really want to hover with these aircraft. It's just enough for you to get off the ground, quickly transition into horizontal flight, and that you want to be done with it. But you see a lot of these configurations fall sort of in between, right? So again, it's a compromise of what type of mission do you want to fly. Do you want to fly far and fast, or do you want to fly slow and have a lot of hovering capability. So if you're talking about like a EMT type mission, you probably do a lot of hovering. So better toward like a tilt rotor helicopter configuration. If you want to go fast and further, typically you'll want a configuration that's something like we saw in the ducted fan kind of case, more like a Lilium vehicle. So again, on the right is this one is a particular Joby configuration. This is actually 6 prop rotors that all tilt at the same time, and so you can see by the diagram that you can vertically lift and smoothly transition. That transition sounds trivial, but this is actually the hardest problem for the aerodynamicist, is to how to successfully take basically a vertical aircraft which has 0 speed, horizontal speed, and then smoothly transition. I mean, the V-22 also took decades, how many decades to perfect, and this is what challenge everybody's looking at. Also, you want to also maintain good ride quality too. So you don't want to have a vehicle, especially for passengers, you don't want to have a vehicle and then have a roller coaster ride, right, as opposed to a transition. So this is another factor. So given all this, what are some of the big challenges, right? So this is all great, we can fool around with all these different configurations, but at the end of the day, what is really the problem? Again, just like electric vehicles, it's the energy storage system, right? And you can see right now on the left, it's the volumetric density. Typically for aircraft, I won't say always, but we're more concerned about gravimetric density of batteries, because weight is a super premium on the aircraft. But you can see different fuel systems from gasoline, propane, various hydrogen, and all of those listed. But you see that batteries are, at least on the left diagram, in that tiny little speck there, right? So it's horrible, right? And this is the problem we have with batteries, right? And how to actually push out the batteries so that we can have flight. So if we look at the right figure, again, this is more talking about the automotive lithium-ion batteries, but again, the energy density and power density is always increasing in this area, improving. But when we're talking about 100 to 200 watt hours per kilogram is typical energy density that automotive uses. Power density somewhere around 1,000, 1,500. It's just barely right now enough to get off the ground. But it is tantalizing. I said it's barely getting off the ground, but you see that it is getting to a point where useful things are happening. So actually, this is actually on an Archer website, who's one of also a company that's building an electric vertical takeoff and landing vehicle. So we have a sort of a modified Brigade range equation. Thing to remember is, in the regular version, if you look at airliners, they burn fuel as they fly, right? So actually planes get lighter and lighter, and they become more and more efficient. Unfortunately for battery electric, this is another drawback. We're not shedding electrons, right? It's always there with batteries, so the aircraft at takeoff and landing is exactly the same. So actually that's another place where we get reduced range. But if we plug in some of these numbers about the efficiency of the aircraft, you see some of the factors like L over D is a big factor. But here in this case about 12, and this is kind of normal for a small vehicle. And we get a cruising range around 60 miles, right? So now it becomes kind of interesting, right? So this is not going to replace, an airliner, right? That's still far, far away, but maybe this could be, enough to fly, let's say, from an airport, from an urban setting, from downtown to an airport, Maybe you could do some commute flights, etc. So this is why it's getting interesting for folks. So now given that, we begin to sort of segment this market. And I would characterize it right now, there's really three big segments that's developing. One is this very short-range urban air mobility mission. So this is like intercity typically. So some people have vision of, again, you don't know how it's going to play out, but maybe from, for example, maybe between downtown, intra-downtown, that there potentially could be. Maybe you have high-rise buildings and you might want to fly from one building to another. So we're typically talking about, 10-mile, maybe less than 10-mile range. And you see that they're more optimized for hovering, right? So this is a short range. They don't fly very fast. Typically, they'll fly maybe 50, 60 knots, and not too fast. And then the middle is this urban air mobility mission. Again, this is a little bit extended, something like 25, 30-mile range, 4 to 6 passengers flying. Again, now from, let's say, from here to LAX. I guess if you look at it from short range, you might fly to Long Beach with a short range vehicle. You might fly to LAX with a longer range urban air mobility vehicle. And then the third area is this regional air mobility. So this is now flying, let's say, from here to maybe up to San Francisco. And it's a little bit bigger vehicle typically, maybe starting from 4 up to about 19 passengers with a little bigger vehicle. Here the configurations are a little bit more diverse in the sense that some believe you can't build a vertical takeoff and then fly this type of mission. You may have to just do more of a conventional aircraft, because it is extremely energy intensive to take off vertically. So you want to conserve that energy. So as I mentioned at the beginning of the talk, Supernal is working on a particular segment, which is the urban air mobility vehicle. And I think I've talked to you a little bit about the characteristics. Typical payload is about 1,000 pounds. This is about 4 to 5 passengers. Again, talk about the distance. And we'll go a little bit more deeper into the different technologies. But a lot of times when we get to the technical section, people always ask me, like, what do you worry about on this vehicle? And I typically answer everything. Right? Everything is a challenge on this vehicle. Right? I will say the absolute number one is the energy storage system, but there are literally hundreds of challenges on this vehicle to bring it to fruition. So it is a daunting vehicle to build. But why are so many people interested in this field, right? So this is actually there's been actually McKinsey studies, and I think this is from Morgan Stanley. And I think Morgan Stanley is actually the most conservative one, right? But they all end up in total addressable market in the 2040s and 50s into trillions of dollars, right? Now, of course, they have to take it with a grain of salt, right? Like, is that really going to happen? I mean, that's what they said about autonomous driving too, and kind of where are we now, right? So you do have to take it with a grain of salt, but there's lots of excitement that this would be next wave. At the very least, I think the most pessimistic is people looking at existing helicopter market, which is about $50 billion market right now per year. So, worst case, it's still a multi-billion-dollar industry, right? But ultimately, we'd like to be into the trillions of dollars. Right? But one thing that I think has been seminal to this industry is Uber Elevate. Now, they have actually disbanded. Uber actually disbanded this group and sold parts of it actually to one of the companies, Joby. But this was sort of a seminal paper actually, this that they released, which is they had all this data from Uber about where people travel and what is sort of the sweet spot of building an electric aircraft, and they did extensive studies, which we're also validating, but it's this Uber Elevate mission, which is again 25, 30 mile. You'll hear about sizing and mission. So you size the vehicle for typically the maximum range you'll fly, but then you have a mission that you will actually fly. So typically you'll hear that the sizing mission is 60 miles, so you'll build a vehicle for basically a range of 60 miles. But the typical mission average flight duration is 25 miles. And so this is what happens, you fly, it doesn't fly that very high. It'll fly maybe a couple of thousand feet in altitude, so we don't actually want to go too high for this flight. It's not far enough that you want to go really high. And basically you land, you recharge, typically for a few minutes, and then you fly back or fly to another destination, recharge, fly. But it's not charged all the way back. So you see down here, I don't know if you can see you see cursor down here, but in the lower right diagram, you see that's the state of charge of the battery. So you use up some of the battery, you quickly charge up, but not 100%, you just don't have time. And then you cycle through it the entire day, and at the end of the day, typically 8 hours or so, you then recharge back up to 100%, get ready for the next day. So that's a typical profile. And where is this going to fly? So this is some of the work that the FAA and the NASA is doing right now. It's a little bit, I won't say 100% agreement, but the way it's trending is that there will be this carve-out of so-called UAM corridors that sort of like highways, like highways in the sky. I think there was an old term back in like 80s or something, highways in the sky. But basically these corridors. It's not too unlike helicopter corridors now. So if you look at helicopter routes, this actually typically follows highways. And you fly these corridors, and it's not that they're impenetrable. So potentially other aircraft could penetrate into this corridor, but this was a way to largely segregate the air traffic from the rest of the larger aircraft in general aviation. And then the other thing is you need places to land. Right? So this is actually may end up being the bottleneck at the end of the day. You may have an aircraft, but if you have no place to land, then it does no good, right? So people are talking about, typically they're called vertiports. You can think of them as helipads, but maybe with more services. So in particular, we also work with this company called Urban Airport, and I think that was at Coventry in England, where they built a full-scale sort of mobile things that you could quickly set up where you can go in and land. So you can think of like a stadium, if you want to go to a Rams game, quickly travel and beat the traffic, you could quickly set some of these things up and you can fly to that destination. Okay. All right. So I'd like to also then now talk about the enabling technology and gaps. And like I said, if you ask me what are the gaps, it's kind of like everywhere. There's gaps everywhere that we have to fill. So as I mentioned before, the first thing and the biggest critical thing are the batteries. And you see, we talked about a little bit about the energy density. So if you look at the top right there, you see kind of where the automotive market is. The green is where we ultimately would like to be, but we also know that's not reality in terms of today's battery technology. So it's going to land somewhere between that blue bubble and the green bubble is where we're trying to target when we try to bring this aircraft into service. So what is the challenge again? Challenge is we're asking for, again, we're basically asking to have the cake and eat it, right? Which is we want high energy density and we want high power density. If you're a battery engineer, you're probably saying, that's impossible. You can't get both, right? You can get one or the other. But if you're asking me for both, I don't know how to do it, right? So, for electric vehicles, typically you're talking about energy density to give you long ranges. Typically they don't have very high power densities. If you're in the market for, let's say, power tools, right? Those things actually have very high power density, but they have very low energy density. So again, it's not completely mutually exclusive, but they're kind of the opposites of each other, right? So we're asking battery suppliers to push the frontier on both sides, right? Which is very difficult to do. And this is the discharge for an eVTOL aircraft, electric aircraft, versus automotive. So the blue is the automotive discharge cycle. Typically, battery engineers talk about C. 1C means discharging the entire battery in 1 hour. So that's the typical you talk about. And you see in typical automobiles, it's actually pretty gentle on the battery. Now you have like ludicrous mode on Teslas and things like that, which does stress the battery, but it's also a very short amount of time. We're talking about a few seconds, typically those acceleration profiles. For us, you see, we are drawing enormous power from these batteries over an extended amount of time. So again, this is very challenging. And also what this does is it destroys battery cycle life, right? And as you know, if you have your phones, more times you charge, and the harder you use the battery, the less cycle life it has. But we're basically killing the batteries every time we fly. So this is, in fact, you may be killing the battery with the current existing batteries in few hundred cycles. Right? A few hundred cycles means that you may be replacing this battery every couple of months on this aircraft, and this is the most expensive component on the aircraft. So this is one of the biggest challenges. The other part is, when those projections about trillions of dollars, that means flying a lot of missions. Right? We talk about that's really like darkening the sky with these type of vehicles, right? And that means how do we get these vehicles to fly in this level of density, right? So we're talking about things like the vehicles need to communicate with each other, avoid each other, how to strategically deconflict them. Again, when we're talking about air traffic control, again, we're talking about tens of vehicles. That's the infrastructure, right? When you have hundreds, potentially thousands of aircraft in the air in a very small airspace, how are you going to manage all this traffic? So this is another challenge that we're working on. Again, NASA has taken a lot of the lead in this, in terms of looking at ConOps. So you'll sometimes hear about this so-called UML, like urban UAM maturity levels, and it really talks about the traffic density and what needs to happen. And again, kind of no surprise here. Again, with the high density of traffic, we have to look at the sense and avoid or detect and avoid systems. Typically categorize them as cooperative and uncooperative. Again, there's some movement in ACAS-X right now. There's XR, which is for rotorcraft, and so there are various variants we're looking at. And also, we're flying in urban areas, so again, CFIT or the collision into objects, fixed objects is also a big concern. So typically we'll have to have some sort of high fidelity map to avoid static obstacles. And again, we have non-cooperative objects. So we're exploring different sensors like IR sensors or camera sensors. We're also working with some partners on compact radars that can see the airspace. And again, we're also flying at a low enough altitude. We have to be wary of like wires and other obstacles that may be in between. And also a lot of these technologies rely on machine learning and other techniques. So to get the accuracy that we need, a lot of times we explore different types of AI and machine learning algorithms for whether it's for navigation, visual navigation. If you had a emergency, if you're in the automotive autonomous driving, you probably see a lot of segmentation. We kind of do it differently. We're looking down, but worst case, we have to land maybe at a tennis court and things. So we're actually trying to potentially may need to segment different terrain on the ground for emergencies. So all of this needs to work, but as you also know, the aviation industry is very conservative, right? So when you go to the regulators and say, I want to put this and certify this AI algorithm, their minds are kind of blown, right? It's like, what are you talking about? Right? How do we do this, right? But there is fortunately some active work in this domain. In particular, EASA, the European Aviation Safety Agency, which is a counterpart to the FAA, is now starting to put out guidelines about how you would certify a machine learning algorithm. So this has been actually very helpful in terms of the direction that they're proposing to start standardizing on how to do this. Again, it's a lot of it is based on actually the data. Again, it's a machine learning. Typically, if you've gone through, let's say, DO-178 process, it's more about the requirements, about the code coverage, etc. When we talk about machine learning, it's about how do you track data, how do you make sure that it's not tampered with. So it's more about the data centric, about how to protect the data. You do have the right set of data. How do you measure whether you have enough training set, etc. Okay. And then the other part is the computing gap. So fine, you want to put all this machine learning algorithms, etc. on the aircraft, but then next question is like, well, do I have any certified hardware that can run any of this stuff, right? And it's like, well, actually, I don't. So this is another issue we have. The automotive industry kind of went through this too, which is, they're typically also behind the consumer electronics, and they've been trying to push, again, for autonomous driving and driver assistance, that you need this so-called SoC. In this context, SoC is not state of charge, it's the silicon on a chip with this heterogeneous compute, which is basically the entire industry is moving towards, right? To have different computing units that are optimized for different computing needs. So typically aviation's, if automotive is typically about a generation behind, we're typically 2-3 generations behind. This is something that we're working also closely with the regulators, and just now some of the heterogeneous chips are being certified or in the process of being certified for aviation needs. So these will be critical to all of the things that we want to do on the aircraft. All right, and then also talking about computing architecture. So you notice that our vehicle is small, and so now we have some powerful chips, and now we have to consolidate everything into small space. And so this is another thing that's driving our architecture. So on the right, sort of the aviation architecture, I think went kind of from a lot of federated boxes. And there were high-speed buses. Now there's kind of this concept of integrated modular avionics. Basically, but we need to take it to a next step. The integrated modular avionics, you see that in modern aircraft, whether they're military or commercial now, but these are still multiple single board computers, plugged in, and we can't even afford that on this aircraft. We have to really compress it down to basically one or two boards. We still have some redundancy, but all the computing now needs to really be centralized, and so that's one of the challenges. But fortunately, again, a lot of these technologies are coming from automotive. Automotive is going through the same transition. Instead of these little boxes everywhere in the car, people are starting to centralize things. So that's also the trend that we're looking at. The next slide is about simplified and autonomous vehicle operations. And actually, this has a lot of implications for navigation, and I'd like to spend a little bit of time because this is a navigation community. So when we talk about simplified vehicle operations, we're talking about sort of what we call non-traditional aircraft controls. And why do we want to do this? So maybe start with why we want to do this. Because when we talk about a lot of these business cases, we need to ultimately have reduced pilot training and ultimately actually get the pilot out of the aircraft. You see, it's a very small aircraft. That seat is extremely valuable to us. So that's the ultimate goal, which is to take the pilot off the aircraft and have a remote aircraft. Of course, it does require some social acceptance. Would you get on the aircraft without a pilot? But the first stage is also have the simplified vehicle operation. So there's already a pilot shortage, and we need to minimize the pilot training on this aircraft if we were ever to scale this aircraft. So when we talk about pilot training, we're talking about simplifying how you fly this aircraft and make it easier to fly. And that's what we're talking about, simplified vehicle operations. Now, SVO means many, many things to many people, because there's no one definition. But for us, I just like to say on the aircraft, it means that there are no pedals, so there's no foot controls. It's translational control and position hold. It's somewhat akin to if you flew DJI drones, right? That you fly, slightly different, but you can tell it to stop and it'll maintain position. You can accelerate. So most of the rate controls, which is the traditional avionics or flight controls today, the pilot is basically commanding rates, right? I want to turn, and when you push, you begin to increase the rate. This is not a rate. This is more direct control of, I want to change the attitude to this. I want to go at this speed. That's what we're talking about. And also has no reversionary mode, and this has huge implications for navigation, meaning that there's no backup. In some vehicles, you may think about backups. Okay, well, if the system fails, I have a backup back to the rate controls, and then the pilot can take over. That's not what we're talking about. There's no reversionary mode. It will always stay in this mode. So what this means is now you have the navigation systems has to be guaranteed. Right? It's up to back to the full safety of the 10 to the minus 9, if that's the safety standard we're building. So you can't have this kind of loss of GPS, or you need an equivalent that will fill in, let's say, for GPS. Right? So this has huge, and it becomes now flight critical. So this has huge implications, and what that means is, and this is why I'm here actually, to learn and talk about, what are a lot of the different technologies out there to make this robust enough that I can put this as a flight critical system, the navigation system as flight critical. Some of the things that we're also and when we talk about now also autonomous, we're talking about R&P performance, again, drastically reduced because, again, we're talking about much higher density. So this is what we need. Of course, very precision. So we can talk about, GBAS and other things. But again, to get to the level of safety we need, we're going to need different redundant navigation technologies. And I'm going to speed up a little bit. Again, communications is another big thing. And we talk about typically two different types of communication, so-called command and control, which is really talking about low latency but very high reliability. And then we talk about typically payload data, which can be typically like over 5G and others, more high-speed maintenance and health data and other things, also maybe training data for AI. And again, all of this also in the backdrop of allocating potentially dedicated frequency spectrum, right? So right now there isn't really, we're talking about really high integrity, high reliability communications from the, not just we're talking about sort of voice, but sending command and control data. That bandwidth or the spectrum has to be allocated. Now there are some companies that are trying to allocate that spectrum for in fact, particularly for this use, and potentially other spectrums for things like vehicle-to-vehicle communications. Okay, and then it all has to come together in this back-end data infrastructure. So this is from NASA, actually, this diagram. Is, how are you going to operate this vehicle, right? So there's this, in the middle you see this thing called a provider of services for UAM, so called the PSU. And these are meant to be sort of the aggregators of different data, provide strategic deconfliction, and they suck in weather data and others from, again, sort of this so-called the supplemental data service providers, and also share, exchange from different PSUs and send them out to the vehicle and the operators. Right? So again, very, very complex system. Again, this is talking about future. This is not the current airspace today, but you can see that there's a lot of work to be done if we want to have the level of density that's required to have this huge market. And then finally, in terms of technology, we also have a manufacturing gap. Right? So when we talk about aerospace, we're typically talking about hundreds of vehicles per year. I mean, that's the high rate, right? I mean, some vehicles are into, tens, maybe a handful per year, right? I think Airbus A320, just before the pandemic, was the highest rate program. I think it reached around 800 aircraft per year. That was the peak. So that's not really going to cut it. And then there's automotive, which they are good at high rate. They're into the millions per year, right? So we kind of fall into this middle. You could call it Goldilocks, but actually, it's, maybe it's more of a valley of death, which is, we can't quite use the aerospace process because, we can't handle these things like at the rate. But we can't also invest in the level of automation that automotive can, because we're not building millions of these a year. So we're sort of right in the middle, and we need to figure out what is the right automation and what needs to be hand-built. So this is something that, now fortunately for us, one of the strengths is Supernal is part of the Hyundai Motor Group, and so this is something that we can leverage, which is from the automotive experience and how to do high-rate manufacturing. All right. And then about to wrap up here. So our Supernal vision, I just wanted to wrap up with a couple of slides here. We have our 4 pillars. So one is safe. We can never compromise safety. This is a nascent market. We believe if we have one accident, this potentially could kill the entire industry. So this is something. In fact, there was actually helicopter service between Manhattan and JFK. It was a common sight, but they had one accident over a skyscraper in the 70s, and basically And it wasn't even the helicopter's fault, right? But it kind of killed that industry there. It's coming back a little bit, but basically that killed it. Quiet, again, that's the other promise, that it's zero emission, but we can make it very quiet. But these type of vehicles, when they're cruising, it will be roughly equivalent of outside traffic. So if you're indoors, you would actually not even hear this aircraft fly over you. That's how quiet we can make these aircraft. Now, there's a little bit of challenge on during landings, how we make it so that it's completely unintrusive, but this is another selling point, which is it will sound nothing like a helicopter, right? So there's like a lot of questions come out, like, well, helicopters exist, why didn't they exist, right? Well, because most people, the noise and everything, just helicopters, people don't want it, right? And that's another thing that it's addressing. Affordability, again, a lot of these things we can make it more affordable. And also passenger-centric, in terms of the smoothness of the ride, etc. That's one of our tenets. And then, it talks about Supernal as part of the Hyundai Motor Group, and I think this is another thing that we strive for, is to actually also create an integrated mobility solution. And I think we're one of the few companies and groups that can actually try to put these pieces together, right? So when we talk about urban air mobility, and our biggest value proposition is time savings, right? You want to jump over traffic and get you to your destination. But what I want to caution is, this is not a door-to-door service. This is not taking you from your front of your house directly to somebody else's house, right? You first have to get to the vertiport, quickly make that transition, fly over there, and go to your destination. The last mile is still there. And we need this very fast and seamless. So it has to connect up with the ground transportation. And this is something that we try to work with the rest of the motor group in terms of how do we piece all these systems together. So I apologize, I talked a lot, but just to summarize, again, we feel, we're really excited that this is the third revolution in electric propulsion system, and which will lead to, many exciting and new different configurations. It may be like the aerospace, 50 years from now, we'll maybe get down to an optimal configuration, but it's a very exciting time where we're exploring many different areas. Batteries, and it's always the batteries right now. And we believe it's going to be a huge market, lots of challenges, but this is where we're reaching out to communities like yourself, all of these areas, right? We really need to continue to develop and mature these technologies. So I hope you found this talk at least interesting. And again, it was it's been a real honor to be able to speak to you. And I have to do one last plug, which is just our website here. We're looking for navigation engineers. You see there are a lot of challenges. So, so if you go to jobs.com, Supernal, arrow, you can see some of our navigation positions open. All right. Thank you so much.
Well, thank you, Sam, for a very interesting talk. Now I'd like to open the floor for discussion, and we can take questions from the audience.
Yes, you mentioned last mile and takeoff and landing bottlenecks.
Mm-hmm.
Have you ever considered personal urban air mobility, like you see in the science fiction movies? A person takes off from balcony and lands on the driveway. So it will take off the problem of landing and takeoff and last mile also.
Yeah. So people have considered that. Now it's defunct, but there was a company called Kitty Hawk, which was actually largely funded by the Google founders, which had that mission, right? Which was the vision was you could put this kind of like on your lawn, right? It was meant to be completely autonomous. You would ride, and then it would go to your, again, autonomously fly to your next destination and then land in someone else's lawn or whatever, right? I think, the technology can get you there. I think it's, again, the challenges of airspace and other management, right? The lower you fly, now it's getting very congested. Potentially will get congested, right? You have drones and, of course you have birds and wires and everything, right? So that's, I think, one of the biggest challenges. Technically, certainly it may be possible.
A few blocks, just to go to the grocery store and things like that, to the office, maybe,
Yeah, and of course, like neighbors might complain also. It's like
they will always complain.
Yeah.
Hi, good morning. I'm Okoye Sechas from German Aerospace. I enjoyed your presentation. There was a lot of good information there. I'm just wondering, how much would a ride to the airport cost if I used one of those?
Yeah. So, we are trying. The goal is to make it competitive to sort of maybe a premium ride share service. So if you talk about some people have speculated, and if you just talk about energy costs and things like that, and then you say, well, the aircraft requires less maintenance because you have electric motors. It's not like a traditional aircraft, etc. Some people have proposed you could get down to like maybe $1 a mile. Now, a lot of people don't believe that. I think it's going to start probably, my guess, is probably around $3 to $5 per mile, which would still be in the range of, like an Uber. Black or something. But that's sort of the goal, which is to be competitive with, with ground transportation. In fact, that's what people say. Well, what's your biggest competitor? It's actually the ground, right? It's the regular taxis and Ubers, to be frank, right? Because, like I said, we were flying 30, 40 miles. If you can get there, if there was no traffic, right? In fact, you could argue that it's cheaper and about the same time you would get there, right? Because you have to make that connection between the vertiport. So that's actually our biggest competitor.
Hi, thank you for your talk. I had a question. I'd like to follow up. You commented on the issue of the batteries with their power density versus energy density, and that you use the term that you basically are thrashing the batteries or destroying the batteries.
Yes.
And so I thought I read that you said after a few hundred charge cycles you have to replace the batteries. Is that correct?
Yes, that is. When we talk about existing technology, that's sort of the lifetime what we're talking about. Right?
So just like if you had 10 charge cycles in a day, that means you'd have to replace the batteries every month?
Unfortunately, yes. Now, we talk about full discharge cycles. So we probably wouldn't do a full discharge like 10 times a day, but we are talking about potentially several per day. And we are, again, with the existing battery technology, we're talking about, yes, within months you may have to replace the battery. And people have also already are thinking about in this type of vehicles, how we're going to recycle all these batteries, right? So what is the second life of these batteries? Do they go to some sort of energy storage grid? What do we put it in EV vehicles? So this is another big factor, or do we just recycle them and make new batteries out of them?
Well, what percentage of the total cost of the vehicle would be the batteries?
Well, we won't. It's a little bit proprietary, but it's a significant portion.
Yeah. So I guess this seems to be a huge challenge to the economics of this. It seems.
Absolutely, this is the biggest driver right now in our operating costs.
Any other questions? Well, I have a question. At least for me, one of the pain points to go to the airport is to go through the security line. Like, how's it going to work? Like, is it going to be completely eliminated, or what's
Yeah.
gonna happen?
So this is another. You said what keeps me up. There's so many things that are keeping me up at night, right? So this is another one, which is, and this is a discussion with the FAA, whether it's going to be classified as kind of like a regular, these vertiports. Would they be classified just like the airports? You have to go through security. Think of the trend is toward that there'll have to be some level of security, maybe some sort of a biometric. But again, it's all these either pain points or barriers that will slow adoption, right? In fact, that's a big concern, that if we have to go through metal detectors, or even, I guess, now even bigger detectors, right? That we'll have to think about this, right? This is something we discussed with the regulators.
Any other questions? Just one more.
Yeah, very nice talk. Thank you very much. Just have a question on the energy source that you are talking about in the future. The UAM, they are like fully electric. Have you ever considered other energy sources like hydrogen or hybrid ones? Because I work in Airbus and we are like trying to push forward on the hydrogen, but I understand that is on big aircraft, but for the small aircraft.
Yes. So we are looking. As part of the Hyundai Motor Group, we are also looking right now at hydrogen fuel cell technology for these vehicles. Now there's, when we talk about hydrogen, there's, sort of two methods, right? Building more conventional gas turbine type engines, or using more like fuel cells to power electric vehicles. Now we're working more on the electric side, not the more the gas turbine side. We believe, for extended ranges like the regional air mobility we talked about, I think the batteries are going to be challenging for these type of longer, especially when we scale up. Talked about 15 to 19 passenger vehicles. So for those right now, we are looking into hydrogen fuel cell technology, but if we go back to the old diagram, hydrogen also has some issues, right? If you looked at it, you looked at the diagram, I think it was on the far right, it has very poor volumetric density. So it has a lot of great energy density, but horrible volumetric density, right? So what that means is it's hard to store this, right, in any sort of system that will fly in the aircraft. And that's just for the fuel itself. So when you talk about, you need this large vessel, that's, and to reduce the volumetric density, then you have to pressurize this thing or put it in liquid form, and all that drives weight, right? So those are the challenges. It's not the fuel cell itself, but how to store the hydrogen is a big challenge. And when you weigh that, again, it falls typically when you end up comparing it to conventional, gas turbine, hydrocarbon fuels, you end up with a heavier propulsion system with the current technology. And so that's also another active area of how to store hydrogen in a more compact form.
Any other questions or comments? Megan, one right here.
Go ahead.
Just wait for the mic so everybody can hear it.
You mentioned FAA certification and their lack of ability to, or knowledge of how to certify certain new technologies and algorithms that you're developing. Do you think that's going to be a massive hurdle for you to get some of this to market, if you have to wait on them, or just see if they can even certify anything for you in time, especially if you have technology that's ready to go?
I hope we don't have any FAA folks in here. No, but actually the FAA has been very proactive in working with the industry players. They don't want to, kill this industry because, and we talk about this industry, in the trillions of dollars. There's also in some sense, sort of different national races, right? That's occurring right now with the European continent, in the U.S. and in Asia, right? It's because they view this as, again, a third wave of air transportation, right? And the incumbents have no advantage here, right? So this is another thing that everybody's excited, and you see small players, etc., right? Because at the end of the day, even the Boeings and Airbuses don't necessarily have a competitive advantage in this field. They know, just as little, right, as a startup right now, right? And so, people feel like, okay, we've got to get in early, we've got to do this, right? And the position from the regulators have been, both from the European side, American side, as well as a lot of the Asian countries, very welcoming in terms of let's work together to figure out how to certify this aircraft, right? It's not that there aren't challenges, right? Some of folks know that recently the FAA kind of changed directions. It was going through a Part 23. A lot of entrants were going through trying to get a type cert through Part 23, Amendment 64. Now they say, okay, no, it's not really a fixed wing. It's a special class. Now they're being routed to 2117B. But the regulators are proactively reaching out, and also we also work with the FAA Tech Center, who are kind of in charge of, how do we introduce new technologies into to the national airspace. So it's really a hand-in-hand collaboration that's needed.
Gotcha. Thank you.
I think we can take one more. It's probably one here.
It seems like this is going to require considerable public investment between navigation, regulation, the vertiports and everything. Why is this desirable over further investment in mass transportation?
Yeah, that's an interesting, very good question. So, part of the argument has been that there potentially could be investment light compared to some of the mass transportation, right? If we're talking about subways and other systems, that we could potentially sort of bypass a lot of the hurdles, right? Now there are still hurdles like, when you try to locate a vertiport. Now most of these also, we are, when we talk about vertiports and stuff, we are still at this stage talking still more about privatization, private people building. The airspace management, again, ultimately the FAA would like to privatize that. Kind of similar to what they're trying to do with the drones, right? It's not a fully satisfactory answer, but some of the argument is it will cost the government much less, in terms of public funds to build out these type of infrastructure, and overall cost of the infrastructure would be lower.
All right. Well, thank you, Han, for the great talk. Thank you. It's very interesting. Thank you. So now we'll have a 30-minute break, and there should be some coffee and refreshments in the hallways, and we'll reconvene at 10:45. Thank you.